Hello, am I audible? Hello, hello.
Yes, sir.
Okay, thank you. Good afternoon, everyone. Welcome to this NPTEL live session. It is the third live session for this course, Introduction to Machine Learning, week 3. My name is Owen Maiti. I am a PhD scholar in the Department of Computer Science and Engineering at IIT Kharagpur. So in this session, we are going to discuss some practice problems on this week's content, which is mostly SVM. So we will discuss some practice problems on SVM, and I will also try to answer your questions, doubts, or queries if you have any. I would also try to answer all your doubts and questions. Is my screen visible? Can anyone confirm? Is my screen visible?
Yes. Yes.
Okay, thank you. One more thing to note is that this is a 2-hour long live session, that is from 3 p.m. to 5 p.m. But Google Meet doesn't allow meetings over 1 hour. So after the first hour, I have to create a new meeting link and I will share that meeting link in this meetings chat. So all of you have to join that meeting link for the second hour, which is from 4 p.m. to 5 p.m. So at around 4 p.m. I will share a new meeting link for the second hour. And please make sure that you click that link first, then leave this meeting, otherwise you will lose this meetings chat. Once this meeting is ended, this meetings chat is lost. So I will share the I will notify all of you about that at around 4 p.m. and I will share that meeting link. So please join that meeting link at 4 p.m. for the second hour of this live session. For those who joined my last live session, I have to make a correction in my slides and presentation in one of the questions. So this was one of the questions that I discussed in week 2 live session, that is the previous week's live session. LDA assumes that class data is distributed as there were 4 options: Poisson, uniform, Gaussian, and LDA makes no such assumption. So in this question the correct answer would be C, Gaussian, but in last week's session I gave a wrong answer. I gave the answer D, but D is not the right answer. C, Gaussian would be the right answer. So sorry for that mistake, but I have corrected it in the presentation, and I'm also announcing this correction in this session. So C, Gaussian would be the correct answer, that LDA assumes that class data is distributed as Gaussian. So this is one correction that I had to note for the last week's live session. So now we will solve some practice problems for this week's content, which is SVM, mostly SVM. I hope most of you have gone through the video lectures, otherwise it would be difficult to understand these question and answers. So this is the first question. So consider one-dimensional data set. X and Y values are given. X is the independent variable, which is the feature, and Y is the dependent variable which we want to predict. So -1 1 0 -1 2 1, these are the 3 points of this one-dimensional data set, and you have to find out whether the following statement is true or false. The statement is the dataset becomes linearly separable after using basis expansion using the following basis function phi x equals 1 x cube. So we are using a basis function to transform this input features, and then we are trying to check if the dataset has become linearly separable or not. I hope the question is clear here, that we are transforming this input feature x using this phi x 1 x cube. So this one dimensional data set, one dimensional data point becomes a 2-dimensional data point now with this feature transformation 1 x cube. So if we do this feature transformation, then whether the data set becomes linearly separable or not. So this is the question. You can write your answers in the chat. So if you just plot this one dimensional data without applying this transformation of phi x, if you plot this data, so this is the 0, this is -1, this is 2, so this point is +1, this point is +1, this point is -1. So if you can see that in this one dimensional data set, this 0 points is not linearly separable, isn't it? Because the -1 point is situated in between these two +1 points. So this data set is not linearly separable with this one dimensional data points. But if we do the feature transformation phi x, then will it become linearly separable or not? Is the question clear here? Anyone?
Sir, do we need to plot this for this function, transformation function, or
Just how I
calculate?
just the way I plotted for the one dimensional data. For each point you have to first find out this phi x, and then you plot it in a two-dimensional plot, and that way you can find out whether it is linearly separable or not.
Okay. Okay.
In this one dimensional data set, it is not linearly separable because this -1 point is situated in between these two +1 points. So this is certainly the data set is not linearly separable. But if we do the transformation now, whether it is linearly separable or not. So has anyone computed this phi x for all the 3 points? So what will be the phi x for all these 3 points? First you have to calculate that thing. So if you calculate the phi x for the first point, which is just x equals -1, so let's call it phi x1, first point. So that will be what, 1 and -1 whole cube. So this is 1 and -1. So this is the first point. Similarly, if you find out phi of x2, that is for the second point, so this would be 1 and 0 only, because x is 0 here. And for the third point, x is 2, so phi of x3 will be 1 and 8, isn't it? So phi x1 will be 1 -1, phi x2 would be 1 0, and phi x3 would be 1 8. So these are the three transformed data points that we have computed. Now if we plot these 3 data points, so if we plot these 3 data points in a two-dimensional plot, so it would be first point is 1 -1, so let's say 1 -1. So here is this first point, then 1 0, So here will be the second point, and 1 8 somewhere here with the third point. So this is how these 3 points would look like on a 2D plot after this transformation. So the first point is labeled as plus positive point, so +1. Second point is -1, and third point is +1. These are the three y values, y levels of these 3 points. Now if you see that still all 3 points are on the same vertical straight line, because phi x1, the first point is 1 minus 1. So this is the first point, 1 minus 1. Second point is 1 0, so this is 1 0. Third point is 1 8, so this is here. So still these 3 points are still not linearly separable, because this -1 point is situated in between these two +1 points. So this is still not linearly separable. It will be separable by a curve something like this. A curve you have to draw something like this, so that all the points in this side would be +1, all the points in this side will be -1, that way. But it is not linearly separable, so you cannot draw a straight line which would separate the plus points and minus points. Is there any doubt in this? So first you have to transform the data points, and then you have to plot all these 3 data points in the 2D plot, and then you have to check whether in the transformed 2D plot the 3 points, these set of points are linearly separable or not. In this case it is not linearly separable, because all 3 points, you can say this 1 1 2 3, all 3 points are still situated on a vertical straight line, and -1 point is situated in between these two +1 points, so it's still not linearly separable. So in one dimensional data set it is not linearly separable, and also after this transformation it is still not linearly separable. So this is the answer, B, which is B was false. So this is false, that points are not linearly separable even after the transformation. So these are the 3 transformed points after the basis expansion or transformation, and then you have to just plot these 3 points and we have to check whether they are linearly separable or not. So in this case it is not. Any doubt in this question? So you have to do this basis expansion or this feature mapping a lot in the SVM, because in SVM for to make these set of data points linearly separable, we have to apply those kernel mapping functions or feature mappings. So this is from that theory. So let's go to the second problem on SVM. Consider a linear SVM trained with n labeled points in R square without slack penalties, and resulting in k equals 2 support vectors. So n labeled points are there in the training data set. R squared means 2D data, it is a 2D data, and we have found out 2 support vectors from the SVM, and n is greater than 100. So by removing one labeled training data, retraining the SVM classifier, what is the maximum number of support vectors in the resulting solution? So from the original data set we have found out 2 support vectors for the SVM, and now we remove one training data from the data set, and now we are again retraining the SVM classifier. So now what is the maximum possible number of support vectors in the remaining solution? So options are 1 2 3 n minus 1 n. You can write your answers in the chat. So has anyone found out any answer in this? So with the original dataset of n points, we have found out two support vectors from SVM, and now we remove one training point from the dataset, and we are training the SVM classifier again on the n minus 1 data points. Now what is the maximum number of support vectors that we can get? Nilima says 2. Why should it be 2, Nilima?
Actually, I think it doesn't depend on the n value, that is the number of training points. Hence, I thought that yeah, it doesn't change. Support vectors may not change.
Okay, but uh, if we were removing one labeled training point, if that point is one of those two support vectors, we remove one of the support vector points, then
Okay.
it might not, we might not have those two support vector points if it is not the support vector, if we remove one of the support vector points. Anyone else? So in case of in general, in if SVM is trained with n leveled training points, then in general the maximum number of support vectors that we can get from SVM is n. So all n training points can become support vector points. It is possible, but generally it doesn't happen, but it is possible that all of the points become support vector points. So what will be the maximum number of support vector points in this case? So if we remove, we are removing one training point. So uh, uh, removing one training point can drastically change the structure of the separator completely. So if we train it on the n minus 1 training points after that, so maximum possible number of support vectors we can get is n minus 1 only. So basically it becomes kind of a new data, new training data set, because one point could be the support vector, one of the support vector points, or some other point, so that the separating hyperplane completely changes. So all the points might become support vector points. So here answer would be n minus 1, that now I have n minus 1 training points only, and all of them can become support vector points, because we don't know the exact data set, so we cannot say. So maximum possible number of support vector points is n minus 1 in this case. So n minus 1 would be the correct answer here. This is the third question. Which of the following are valid kernel functions? A 1 plus x, so this is inner product or the dot product. I hope all of you know. So this x comma x dash, this thing is nothing but x dot x dash, or you can write it as x transpose x dash. So these all these three represent the same thing, the dot product between these two vectors. So 1 plus x dot x dash whole to the power d. Option B is tan h, hyperbolic tan, of k1 x dot x dash plus k2. C is exponential of minus gamma, second norm of x minus x dash whole square. So which of these following are valid kernel functions? Asha says B, 10 each. What about the other two options, A and C? Any other answers in this? Nilima has written A, the first one, 1 plus x dot x dash whole to the power d. So I've got two answers so far, A and B. Is there anyone who thinks it would C would also be one of the answers? So here the all three can be valid kernel functions if you follow the video lectures. It is already shown there that all three functions given here A, B, C are valid kernel functions. So the first one is an example of polynomial kernel function. This is simple polynomial of degree d we are considering. And second one is the hyperbolic tangent function, which is also shown in the video lecture, that this is one of the valid kernel functions. And the third one, it is the Gaussian kernel function, exponential of minus lambda x minus x dash whole square. So this is Gaussian kernel function, and this is also one of the most popular kernel functions. So all three are valid kernel functions. So here the answer should be A, B, C, all three. Yeah, answers are A, B, C for this. So now question 4. Consider an SVM with a second order polynomial kernel. So kernel 1 maps each input data point x to k1x, which is x square. So x is mapped to x square, two dimensional data points. And kernel 2 maps each data point x to k2x, which is 3x square. So this also transforms a data point x to a two dimensional data point 3x square. Now assume that hyperparameters are fixed. Which of the following option is true? So there are three options. The margin obtained using k2x will be larger than the margin obtained using k1x. So the margin, I hope most of you already understand what the margin is. So margin is the distance of the separator or the decision boundary in case of SVM from its closest training data point. That is that distance is called margin. So the margin obtained using k2x will be larger than the margin obtained using k1x. Option B is the margin obtained using k2x will be smaller than the margin obtained using k1x. And option C is margin obtained using k2x will be same as the margin obtained using k1x. So margin in which case would be larger? So this is the actual question. So points there are two kernels are used. For the first kernel k1, points are transformed to the two dimensional data point x square, and for kernel 2 the points are mapped from x to 3x square. So you can simply see that this kernel 2 is actually 3 times the kernel 1. Basically just 3 has been multiplied to the two features in this. So now which of these three options would be true, that the margin in which case is higher? Mahadev has written A, which is k2 will be larger than the margin obtained using k2 will be larger than margin obtained using k1. Nilima also thinks it would be A, and Asha has written B, which is the margin in K2 is smaller than K1. So I've got two answers. Two of you have written A and one of you has written B. Any other answers? Does anyone think C would be the right answer, that the margin would be equal in both the cases? Or A or B, which one would be true here? So as you can see that in K2 is nothing but 3 times K1, isn't it? K2x is simply 3 times K1x. Here we are just simply multiplying 3 to the kernel mapping of K1. So for every point we are multiplying this 3. So that means all the points are mapped 3 times, mapped to the two dimensional 3 times. So that means the margin would become 3 times in case of K2, isn't it? Margin is just the distance between the separating hyperplane and the closest point, and if the so the points are mapped using this K1 and K2. So for all the points we are doing this transformation. So margin is just the distance between the point and the separator, so it would also become 3 times than K1, isn't it? So the margin obtained in K2 will be larger than the margin obtained using K1. So this would also in case of K1 the margin would be higher than K2. Sorry, the margin obtained using K2 would be larger than margin obtained using K1. So A would be the right answer here, because we are multiplying this 3 with the kernel for mapping of the first kernel. So the margin would also become higher in this case. So solution would be A, because since K2x is thrice that of K1x, all the distances in K2 space are thrice as big as the distance in K1 place. So that means the margin, which is roughly the thickness of the separating hyperplane that the SVM learns. So this is nothing but the distance in that feature space. If the feature space is thrice that of the feature space K2 is thrice that of the feature space K1, so the distances in that feature space would be thrice that of K1. So margin would be is thrice as big in case of K2. So A is the right answer. Now moving on to the question 5. State whether true or false the following statement. After training an SVM, we can discard all examples which are not support vectors and can still classify new examples. Is it true or false that after training the SVM, we discard all the examples which are not support vectors, we just keep only the support vector points? Now can we apply SVM for testing or classifying new examples? Is this statement true or false that we can discard all the examples which are not support vectors and still we can classify new examples using that SVM classifier? Or SVM needs all the training points to be there to classify new data points? Asha has written true. Any other answers? So do we need all the points, or we just need the support vector points for classifying new examples? Nilima has written false. So I've got both the answers, true or false, in the chat. Any other answers in this? So if you recall, what we have done in SVM is that someone has raised his hand, I think. Did anyone raise his or her hand?
No, 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 correct.
Okay. So in so what we have learned in SVM is that in case of SVM, uh, the we try to find out the separating straight line, basically the coefficient for the uh, linear separator, and if the coefficient the straight line looks like beta transpose x plus beta 0, so this beta is the coefficient and this is the intercept. So we try to learn this beta and beta naught, and this beta can be, if you have followed the video lecture, so you can recall that beta can be written as summation of alpha I yi xi, I belonging to support vector points. SV is support vector points. So we just need to retain the support vector points and we can construct this coefficient beta, and we just need that. So we don't need all the points to classify or test on newer data points. So we just need to retain the support vector points. For all other points, this alpha I is 0 for non support vector points, and it is non-zero only for support vector points. So that's why we just need the support vector points and we can construct this beta, and once we get the beta we know the straight line, and we just need the straight line for classifying the new points. So we don't need all the points. Once the SVM is trained, we just need to retain these support vector points and we can construct this beta, the coefficient, and from that we can classify any new data point. So this is true. So we just need the support vector points for classifying new training examples. So these are the support vector points, act like the parameters of this SVM. So once we have found out which points from the training dataset are support vector points, we can retain them and we can use those for classifying newer examples. So this is true. I hope this is clear to all of you. So now coming to the question 6. Suppose you are dealing with a 4-class classification problem using logistic regression, one versus all method. So we are using one versus all method for this 4-class classification problem. So there are 4 classes, class labels there in the training dataset, and we are using the one versus all method for this logistic regression. So how many classifiers do we have to train if you use this one versus all method for logistic regression? So options are 1, 2, 3, 4. Pavani has written D, which is 4. Any other answers?
Sir, what is one versus all method, sir?
Normally the logistic regression is for two classifications, isn't it? 0 or 1. So logistic regression is designed in such a way that it can generally be used for two classification problems, 0 or 1. But if we want to apply logistic regression for multi-class classification problems, there are multiple classes, more than two classes, 3, 4, 5, that way. So we can employ this one versus all method. So in one versus all method, let's consider there are three classes, 1, 2 and 3. So we will build multiple classifiers using the logistic regression. So we will build one classifier. Let's say classifier 1, where we just classify whether it is the data point is 1 versus 2 or 3. In the second classifier, we try to classify whether it's 2 versus 1 and 2, 1 and 3. And in the second, we train another classifier 3, where we try to find out whether it's 3 or 1 and 2. So this way because logistic regression can only be one logistic regression classifier can only be used to classify between two classes, isn't it? So we cannot apply it for more than two classes. So we put it one versus all, that is one class in one side, all the other classes in the other side. So that way this first classifier we train it on 1 versus 2, 3. 1 is the class 1, 2, these two are class 2 and class 3. Similarly, we train another classifier 2, where class 2 is against 1 and 3. Similarly, classifier 3 is class 3 against class 1 and class 3 versus class 1 and class 2. So 1 versus all, or it is called 1 versus rest. So one class in one side, all the other classes in the other side. That way we build multiple classifiers, and then we combine their results to find out the actual level, whether it's 1, 2 or 3. So if we employ this same thing for 4 class classification problem, so how many classifiers do we need? So is the multi-class classification, that is one versus all method, clear to all of you?
Yes, sir.
Okay, so using the same principle, how many classifiers do we need for this 4 class classification problem? So Binod Govindan and Dr. Mahadev had written D, which is 4. So in case of 4 class classification problem, this is the same way we did it for the 3 classes, that we put one class in one side and all the other classes, rest of the classes in the other side, that is 1 versus 2 and 3, 1 versus 1 and 3, 3 versus 1 and 2. That way 3 classifiers are trained, and then we combine the results of these 3 classifiers to find out which is the actual which should be the actual class level for a new training example. Similarly, for 4 classes 1, 2, 3, 4, we will build 4 classifiers. For the first classifier, we will have it 1 versus 1 versus 2, 3 and 4, and another classifier 2 versus 1, 3 and 4, 3 versus 1, 2 and 4, and 4 versus 2, 1, 2, 3. So this way 4 classifiers will be built for 4 different classes, and then we can combine or aggregate the output of these 4 classes to find out the final output. or the final class level that we will assign to the new example. So here the 4D would be the correct answer. Is there any confusion in this question, in this 4 class classification?
No, sir.
Okay. So we have almost completed the first hour, so I have to create a new meeting link, otherwise this meeting is going to be automatically over after 5 minutes or so. So I'm creating a new meeting link and sharing it in the chat. Yes, so I have created a new meeting link and I have shared it in the chat. So everyone please go to this new meeting and join the new meeting, and I will wait here for 2-3 more minutes so that all of you can copy this link or go to this link, and then I will end this meeting and join the new meeting. So all of you go to this new meeting, otherwise you copy this, you can copy this meeting link or directly go to this meeting and then leave this meeting, so that you don't lose this meeting link from this meeting chat. I can still see 5-6 persons in this chat. Please leave this meeting and join the new meeting. I've shared the meeting, same meeting link again. Please join the new meeting. I'm joining the new meeting in a few minutes, so that all of you can get this meeting link. Then I will leave this one, end this meeting and join the new one. Hello, am I audible? Hello, can anyone confirm?
Yes, sir.
Is my screen visible?
Yes, sir.
Okay, thank you. So this was the sixth question that we discussed. So the answer is D4. So basically, for n class classification problem using logistic regression or even using SVM, whichever classifier you use, for which the generally we train it for two classes. For all those classifiers, we would have to build n class. We have to train n classifiers for n class classification problem. Let's go to the seventh question. Below are the labeled instances of two classes and hand-drawn decision boundaries for logistic regression. A, B, C, three plots are given here. Which of the following figure demonstrates overfitting of the training data? So three classes are given, three plots are given, and you have to find out which one is suffering from overfitting of these three. So Dr. Mahadev has written C, third plot. Any other answers in this? Nilima has also written C. Pravakaran also says C. So all of you have said C so far. So overfitting basically means that we pick the classifier. The classifier is so complex that it tries to minimize the training error to almost zero, but it doesn't think about what would be the generalization error or the test error. So it tries to make the training error as small as possible, and the decision boundary or the classifier in that in case of overfitting is very complex. So from these three plots, you can see that the third plot here the curve is very complex. That is, it is a very higher order polynomial it had chosen, so that it is able to classify all the training points correctly. So the training error has become very small in case of the third plot, but in case of A and B there are some training errors. A is just a linear separator, and B is a relatively lower order polynomial, and C is a very higher order polynomial, so that the training error has become zero. So overfitting occurs when the training error is very small but the test error is very high. So in this case the answer would be C, that the training error has gone to zero for the third plot. So C is the correct answer here. And can anyone say which one of these three is suffering from underfitting? So all of you have written A for underfitting. So the underfitting means the the training error is very high. Training error itself is very high, so obviously test error is also expected to be very high. So in the out of these three plots, we can see that the in case of A, the decision boundary is very simple. It's just a straight line. So in this case, the training error is very high. There are many these red points present outside its region, and also there are some of these white points present outside of its region. So the training error is very high in case of A. So the classifier in A is suffering from underfitting. So A would be the right answer for underfitting, and for overfitting it's C. So answer would be C here, that the decision boundary is very complex and unlikely to generalize the data. So C is suffering from overfitting, and as I've shown that A is suffering from underfitting. So this is a related question to the previous one, question 8. So for the same three plots that we used for the previous question, what do you conclude after seeing the visualization in the previous plot? Multiple answers may be correct. So there are four options. First is the training error in the first plot is higher as compared to the second and third plot. Option B, the best model for the regression problem is the third plot because it has a minimum training error. And option C is out of the three models, the second model is expected to perform best on unseen data. Option D, all will perform similarly because we have not seen the test data. So these are the four options. Which of these four should be correct? Multiple correct answers might be there. So many of you have already written the answers in the chat. Oikendrajit has written A and C. Nilima, Dr. Mahadev, Pavani, all have written A and C. So all four of you have written A and C. So this one and this one. What about the other two options, B and D? Is there anyone who thinks any of the other answers should be correct? Pravakaran has written D. All will perform similarly because we have not seen the test data. Any other answers? Okay, so here the first option says that the training error in the training error in the first plot is higher as compared to the second and third plot. So as we have already discussed, that option A is suffering from underfitting because the decision boundary is very simple, so simple that it is not able to classify most of the data points, many of the data points. So the training error in this plot is very high. And what about B? So in the plot B, so as we can observe from this plot is that it is slightly better than B in terms of training error. So training error is lesser than what we have in case of A. Some of the points have been taken care of, and so it is B is doing a better job than A in terms of training error. And in C, the training error is very low, because training error is 0 from these points, because it is classifying all the data points perfectly using this very complex very higher order polynomial. So the training error is higher in case of first plot, is higher than the other two plots. So first option is correct. Option B says that the best model for the regression problem is the third plot, because it has minimum training error. So it is suffering from overfitting, and the training error is minimum. As we can see, it is 0. Training error is 0 in this case, but as it is suffering from overfitting, so it is also not the best choice, because it is using too complex curve, and the generalization ability of this curve is very low. It is very it is not very tolerant to noises. These points can be noises, these 2 points, but still it is classifying, trying to consider these points and try to make this curve very complex. So this is suffering from overfitting. This is not the best choice for the regression model. And third option says, out of the 3 models, the second model is expected to perform based on unseen data. In case of B, the training error is lower than A, but slightly higher than C. But the curve is not very complex; it is simpler. So it is not suffering from both underfitting and overfitting. So it is not suffering from these 2 problems of high bias or high variance. So that problem is solved in this case. So from that point of view, we can say that B is the best choice. So B is the best model that we can pick. So this second model is expected to perform based on unseen data. That is, its generalization ability would be much higher. So its test error or generalization error would be lower than the other 2 models, A and C, and which is why we expect it to perform better on unseen data. So the C option is also correct. And D, all will perform similarly, because we have not seen the test data, which is not exactly correct, because whatever the test data is, it would somehow follow the trend of the training points to some extent, and from the training points we can see that the generalization error or the test error would be much lower in case of B, as it is not suffering from overfitting or underfitting. So all 3 are not going to be same on the test data. We can say that B is expected to be better than the other 2 models on test data. So D is also not correct. So A and C are the 2 correct answers here. This is a multiple correct answer, correct answer question. So A and C, these are the 2 correct answers. A and C. Question 9. This is on SVM. So one table is given which contains the alpha values, support vector points, and the y values for the support vector points. So these are the we only have the support vector points here and the corresponding alpha and y values for the support vector points. So this alpha is this Lagrangian multiplier, and y is the class levels, and support vector points are the points that we have found out from the support vector machine, for which this alpha value is not 0. So we have to compute the coefficients beta of the linear separator without the intercept term. We are not computing the intercept term, we just have to compute the coefficients, all the coefficients beta for the linear separator, for if we use SVM. So what should be beta? So you have to do a lot of calculations here. You can take your time. If you have already studied the video lectures on SVM, this is not a very difficult question. This is rather easy. So has anyone computed the answer here? So does anyone know how to compute this beta from this alpha and the support vector points and y?
So do we need to use the beta formula for this?
Beta?
Beta formula from the Lagrangian equation, they have given a beta equation here,
Yeah, so
alpha I y xi.
yeah, what is the formula? Beta equals?
Theta equals to sigma I equal to 1 to n alpha I yi xi.
Yes, yeah, that is the formula. So apply this formula on this support vector points and compute it.
So here support vector is given as 3 values, which means the summation has to be applied with these 3 points or what?
No, I mean the expression there is beta equals summation of alpha I yi xi, isn't it?
Yes, sir.
So xi can be a vector, it can also be a scalar. In case of this, xi are these support vector points.
Okay.
Yeah, so this is a vector. So just how you do the scalar multiplication on vectors, you can do that, and then addition of those vectors.
Okay. Okay.
So Nilima has written 1 minus 0.5 minus 1. I think you have made some mistake in the calculations. I think this should not be the right answer. We know there's written 1 minus 2 3.5. This also doesn't seem to be right. Vinod's answer also doesn't seem to be right. The formula is beta equals summation over alpha I yi xi for I equals 1 to n. And this alpha values are given here, this y values are given here, and the support vector points are the xi values. So if we calculate, so the first for the first point, alpha is 1, y is also 1, so this is simply xi. So 1 minus 1 1 plus for the second point, alpha is 0.5, y is minus 1, and then the 0 2 minus 1, so it would be first point is 0, second one is 0.5 and 0.2 1 and minus 1 minus 1, third dimension would be minus 0.5 minus 1 minus 1, so 1 and this 0.5 plus. Now for the third point, the alpha is 1 and y is minus 1, so this is minus 1, it is 1, and this would be 0, this would be 1 2 to minus 2. Now so we have got 3 vectors and we just add these 3, so it would be 2 comma minus 1 0, so minus 2 minus 2 and 0.5 and this is 1.5 minus 2, so minus 0.5. So 2 minus 2 0.5, this is what I am getting. Is there any mistake in my calculation? If you find any mistake, please let me know here. So Binod has again written 2 minus 0.5. Shouldn't it be 2 minus 0.5, Binod? I think it should be 2 minus 0.5. You just have to multiply alpha and this vector point and this y value for all 3 and then add that up. Is there anything wrong in my calculation? So what I am getting is 2 minus 0.5. So basically you have to use this formula and then calculate the beta values using this formula. So does anyone have any doubt or confusion in this? If someone doesn't understand how we are computing this, please let me know now. Yes, so you have to use this formula and beta would be 2 minus 0.5. 10th question. Suppose we have 4 training examples in 2 dimensions. Positive examples are x1 which is 0 0, x2 which is 2 2, and there are 2 negative examples, x3 which is h comma 1 and x4 which is 0 comma 3, and we consider that h is a parameter between 0 to 3. So x3 is h comma 1, so this h belongs to 0 to 3. So two positive points, these are two positive points, x1 x2. These are two negative points, x3 and x4. These are the four training examples we are given. And how large can h be so that the training points are still linearly separable? So what should be the value of h, or basically the range of the value of h, such that the points are linearly separable? So you can plot these 4 points and try to visualize what should be the value of h so that the points are linearly separable. So points are two-dimensional points, so it's easy to plot it in a 2D coordinates plane. So plot these 4 points. There are two positive examples, two negative examples, and try to see in which case we are able to get a linear separator, and then try to find out what is the range of the value of h. So Dr. Mahadev has written 2. It should be a range of values. It should not be a fixed point 2, because h can take any value from 0 to 3. So ideally I am looking for a range for the value of h, 1 to 2. Any other answers in this? Has anyone else come up with any answer? Zero to 1. Asha, Pavani have written 0 to 1. Vinod has written 2 to 3, 2 comma 3. Nilima has written 1 comma 3. So many different answers. Nilima changed his answer to 1 comma 2. So let's plot these 4 points and then we will see what would be the correct answer. So first we plot the two positive points. So 0 0, this is one positive point. 2 2, this is one positive point. And then negative examples at x3 h comma 1. So let's plot the x4 first. 0 3, 0 and 3 somewhere here. 0 3. And h1, so h we don't know, and it should be 1. So it should be on this line. If this is 1, if this is the line y equals 1, so on this line somewhere it should belong, because it is h comma 1. H can take any value between 0 to 3, so it can be from this point to this point. So between these two points it can lie anywhere. So we want to we want these points to be linearly separable. So it would be linearly separable if so this is the line joining these two positive points. If the x3 point lies somewhere here, somewhere here, this is the point, the new x3 point, then it is linearly separable. But if the point lies here, then it is not linearly separable, isn't it? So we want this point to be on the left side of this straight line, this blue straight line, isn't it? If the x3 point is to the left of this blue straight line, then it is then the points are linearly separable. But if the point is to the right of this blue straight line, then it is the points are not linearly separable. So we just have to make sure that the point x3 is to the left of the this blue straight line. And so what is this point? So this point is 1 comma 1, this point, the point where this blue straight line is intersecting with y equals 1. So h can be less than 1. So h can be anywhere in this place. So h cannot be more than 1. If h is more than 1, then the point this x3 point would be to the right of this blue straight line. And if h is less than equals 1, the point is to the left of this blue straight line, and then the points are linearly separable. So Vikendrajit has written h greater than equals 0, less than 1. Yeah, so it's ideally, so h should be less than equals 1. If it is the less than equals 1, then the points are linearly separable. So it should actually be h less than 1 only. If it is h less than 1, then it is not situated on this blue straight line, then it is perfectly linearly separable. So that should be the correct answer, h less than 1. Is there any doubt in this? Yes.
So in the plot that we have taken, the separating line passing through the origin, right? So can't we take the line as an intercept form passing through some x equal to 3 and 0 3 as the 2 points?
This blue straight line is not exactly the separator I am drawing. So if I'm just drawing this blue straight line to show you that if the point is if the x3 point is to the right of this blue straight line, then are the points linearly separable in that case? If this is the, let's say this is the x3 point, then are the points linearly separable in that case? Because the x4 is here, this is x1 and this is x2. So these red points are positive points and these green points are negative points. In that case it would not be linearly separable, isn't it?
Okay.
Because we have to draw something like this to classify them, separate them. But if the point is oh, if the point is to the left of this blue straight line which joins the two positive points, then it is linearly separable. For example, this point, let's say this is the x3, this point, then it is simply separable by the any straight line like this, or this, even the blue straight line is also separates this these two set of points. So this blue straight line is not exactly the separator that I am drawing. I am trying to show that if the points are to the left of this straight line, then the this set of points are linearly separable, otherwise it is not.
Actually, my doubt is if I have drawn the plot in an intercept form,
Yes.
wherein the 2 points, that is 0 0 and 2 2, are on to the left side, and 0 3, and if we take h as 3, it's lying the other side of that intercept line.
Yeah,
That's
if
what
if
happens.
if h is 3, then this point, the x3 point would be somewhere here.
And 0 3, if we draw the line over there, if we
If
draw
it is
this
0 3, then these
separating line for these 2 points, that is 0 3. 0 3 is 1 point, right, sir? Negative point 0 3 is
yes,
there.
yes.
If we take h equal to 3, it's going to be, suppose 3 comma 1, if we draw that, the line is going to be like this, right? Sir?
Mm,
Join that. In that case, 2 positive points are to one side, and these 2 negative points are on the other side.
no, 1 minute, let me draw it in a new plot. So this is 1 point, and let's say this is 1, this is 2, this is 3. 1 2 3. So here would be the x2, and here would be x3, and 3 1. So it should be here. So this becomes this is x1, this is x2, this is x3, this is x4. Okay, so in this case it is not linearly separable.
Okay. Right.
Yeah, because you have to draw something like this to separate these two, isn't it?
Yeah.
These two are not linearly separable. So that's why this point has to lie in this region.
Yes, yes.
Then a straight line can separate these two sets of points.
Okay.
Yeah.
Okay. Thank you, sir.
Okay. So here the answer would be h less than equals. It should actually be, I think, less than 1. If it is equals, then it lies on this blue straight line. So it should ideally be h less than 1. I think I have to change this one. So it should be h less than 1, and h is also greater than equals 0. So you can put that condition also. So h is between 0 and 1. This is the 11th question. This is the last question of this session. So a kernel function k x comma z measures the similarity between two instances x and z in a transformed space. For a feature transform x to phi x, the kernel function is k x z equals phi x dot phi z. So this is a dot product between these two vectors phi x and phi z, and this gives the value for the kernel mapping. Consider the two-dimensional input vectors x equals x1 x2. So there are two dimensions or features x1 x2 for the input vector x. So for the kernel function k x comma z equals 1 plus x dot z. So this is a kernel function that we define. So what is the corresponding feature transform phi x for this kernel function? So that the k x comma z would be phi x dot phi z, which is 1 plus x dot z. Yes, this one. So what should be this phi x? There are four options given. So can we split this 1 plus x dot z, this thing 1 plus x dot z, into something like phi x dot phi z? So has anyone come up with any answer? If we can split 1 plus x dot z into this phi x dot phi z, d 1 x1 square x2 square, but the square term is not present in 1 plus x dot z, isn't it? Then how can we deal with these squared terms, because the square term is not present in the kernel function?
So this 1 plus xz can be written as x plus x square z, sir.
X plus
X square multiplying by x.
no, why do you multiply with x here?
Now to transform that into phi of x into phi
So
of
you
z.
have to find what is the phi of x that we can using which we can
Apply.
write this kxz.
Okay.
So you don't have to make the transformation, you have to find out which transformation can be used for this kernel. So you have to first use this x equals x1 x2. So x is a two-dimensional vector. Similarly, z would also be a two-dimensional vector, z1 z2, and then do this dot product, and then plus 1 is also there. So in this case kx comma z, so this can be written as x1 x2 plus z1 z2, because x is x1 comma x2, this is given here, and z is also similarly another input, which would be z1 z2. So and dot product, so 1 plus x1 x2 z1 z2, we can represent it like this, and then we can write it as x comma x1 comma z1, sorry, x comma x1, sorry, I have written it wrongly, this is dot product between x and z, so this would be x1 z1 and x2 z2. So 1 plus x1 x2 dot product 1 comma z1 z2. So if we do this dot product, we are getting the same thing, 1 comma x1 comma x2 dot 1 comma z1 comma z2. So we are getting the same thing, 1 plus x1 x2. So this can be written as phi x, this can be written as phi z. So phi x is the option B, 1 x1 x2. So we can use this transformation. So this kernel function corresponds to this transformation. Is there any doubt in this? So we have to find out which feature transformation is corresponding to this kernel. So this phi can be this phi x corresponds to this 1 plus x dot z. X is x1 comma x2, two-dimensional vector. Z is also two-dimensional vector, z1 comma z2. And we do the dot product, and then we can split it as this phi x and this one and this one. Is there any questions or doubts in this? So B phi x 1 comma x1 comma x2 is the correct answer. Yeah, so these were the questions that I wanted to discuss today in this live session. So if you have any questions or doubts regarding any of these questions or any other topic, you can ask me now. Does anyone have any other questions or doubts regarding this week's content or anything? Okay, so thank you everyone for joining this meeting. Thank you everyone for joining this meeting. I'm ending this meeting now.